So the next figure is to start explaining to you what are neural networks. So they're simply interconnections of neurons to process information and to produce a behavioral response. The capabilities of real neural networks have been revealed using artificial neural networks to reproduce human behavior like speech recognition. So this figure provides a simple example of how neural networks function. This network includes 3 input neurons. So we can see down here, there are 3 input neurons. So there are 3 input neurons. These connect to 4 interneurons, which will be used to convert the activity into an output activity. So there's a single output neuron. You can imagine the inputs as photoreceptors, each one receiving some light, and the purpose is to decide whether the output neuron should close the eyelid. So you could use that analogy to understand what's going on. Now, you can see at the bottom that there are 7 sample input patterns. So there are 7 different examples. 0 means no activity, 1 means activity. Or in this case, if you consider this to be photoreceptors, 0 means no light, and 1 means light impinging onto the photoreceptors. Now, the purpose of this is for the circuit to convert these input patterns into the desired output patterns. So we could see the desired output patterns. Currently, the network is drawn using example 4. So 0, 1, 0, you can see here off, on, off. And the desired output is 1 or on, and that's what we see here. So it has successfully converted example 4 into the correct output. That's what this circuit has done. It also can correctly convert all of the other 7 examples. I will show you that later. So the key here is to understand the mechanism of information processing, and it depends on the size and sign of the synaptic connections. So it's the effects of the neurotransmitters, whether there's a strong or weak postsynaptic effect. It could be an inhibition or it could be excitation. So whether it's excitatory or inhibitory is shown on the figure by the color. So a red axon means that it has an inhibitory effect on the postsynaptic neuron. A green axon means it has an excitatory effect on the postsynaptic neuron. Now, the width of the axon indicates the volume of neurotransmitter released. So if the width is narrow, that means there's very little neurotransmitter released. In this case, very little excitatory neurotransmitter. But if the axon is wide, that means it releases a lot of neurotransmitter on the postsynaptic membrane. In this case, it's a lot of inhibitory neurotransmitter that's released to produce a very strong inhibition on the postsynaptic membrane. So the mechanism is by the size and sign of the synaptic connections. Now, this is an artificial neural network. So how did they find the right size and signs in this artificial network? Since we don't know what parameters to use, the way we do it is that we simply assign the size and signs randomly. So we use a random number generator to determine what the size and sign of neurotransmitter we should put. So if you get a random number, let's say the random numbers vary between -1 and 1. Well, if you get 0.1, that's a very small excitation. If you get 1, that's a really strong excitation. If you get -0.1, that's a very small inhibition. If you get -1, that's a very strong inhibition. So you use a random number generator to make the connections in the network. As you can imagine, if you make the connections randomly, you don't expect it to solve the problem that you have. So if we look at the top right here, and we look at the error, we see that our initial network, based on random connections, produced a lot of error. We put in the input patterns, and we were getting the wrong output patterns. So we need a learning algorithm to improve the network. The way we do that is very easy. We simply choose any connection. So for example, we could choose this synaptic connection. And what we do is, to the randomly selected size, we simply increase it by 1%. So we increase it by a very small amount, let's say 1%. And now we retest the network. So if by retesting the network, we realize that the error dropped, well, then we keep the change that we made. But if the error got worse, then what we do is that we, instead of a 1% increase, we apply a 1% decrease. So it's by trial and error that we adjust the network. And if we continue doing this, eventually we end up with a network that has learned to solve all of the connections. And I'll give you an example of that later. So you could see here that the learning algorithm, by trial and error, is producing gradually a drop in the error towards the end. And at this point here, we have a network that works extremely well at being able to solve the problem. Since we're doing this randomly, we could imagine that we could simply test every possible permutation, and that will allow us to figure out what the proper network should look like. So for you to understand that, I'll give you an example. If we had a lock, so let's say we have a padlock. So we have a padlock that is used for your gym locker, and this padlock is a very simple one. It only has 2 dials, and all you have to do is dial in the right numbers and you unlock the lock. So let's say it has only 3 numbers. So it has 1, 2, and 3. So if it has only three numbers, then it's going to be quite easy to figure out the solution. So the solution essentially will be 3 to the 2. So there are three numbers on a dial, and there are two dials. So 3 to the 2 equals 9. So there are only 9 permutations. If it takes you 1 second to test the permutation, then within 9 seconds, you'll have cracked the lock and you'll be able to get into the locker. Now, for the network here, what we have is 7 neurons. So the 7 neurons correspond to the 7 dials. So now the range that a neuron can have is from 0 to 100% activity. If we assume that it's 5% change that is noticeable, then from going from 0 to 100 by steps of 5%, we have 20 different levels. And that produces quite a large number. It's 1.28 e to the plus 9, which is a very large number. And if it takes you 1 second to check each permutation, then you'll be done in 41 years. So the reason we do not test every permutation when trying to find the solution in a neural network, that is because it takes too long. We use this method of trial and error because it is feasible to find the solution within our lifetime. I'll now show you an example of a network that is learning. So what you see here is the same network. At the bottom left here, you see the input that is applied. So 0, 1, 1, you could see that it's off, on. And what is desired is 1, but we made random connections. So this is wrong. This is 0.45. And as I play the video here, you'll see that the inputs will change. The outputs will always be wrong. So you can see that at the beginning of the video, the outputs are always wrong. So in this case, it's 0.56, but it should be 0. Here it's 0.53, but it should be 0. Here again, here it should be 1, but it's 0.51. So these are all wrong. Now let me accelerate the video. So you're going to see the changes in the synaptic release. So the trial and error algorithm is adjusting the network. It's increasing the weight of or the synaptic connections. And if that improves the network, it keeps it. If it makes a change that makes the network worse, then it reverts that change. So you can see that there are a lot of changes occurring in this network. And now I will stop it and we'll go at a slower speed. And you'll see that it most likely has learned the patterns at this point. So here we have 0, 1, 1, which is off, on. The desired output is 1, and the actual output is 0.99. This is as good as it will get. This is very good. Let's continue and see what happens for the next patterns. It should be 1 and it's 0.99. It should be 1 and it's 0.99. It should be 1 and it's 0.99. It should be 0 and it's 0.01, which is perfect. It should be 0 and it's very close to 0. It should be 0 and it is 0. So you could see that by simply changing the synaptic connections, you end up with a neural network that is capable of converting the inputs into the correct output. Now, there are some key points to understand about neural networks. You can see here that there's this local minima. There's another one here. This is a problem for a neural network because as you're going down here, you know that the error is getting better, or the error is dropping. So you know you're going in the right direction. Here, to get to this point on the right, you're going to have to increase the error, which is a problem. So you have to change your tactic. For example, in this case, instead of increasing by 1%, you have to increase by 10%. So you have to change your strategy of learning to overcome this area where you're stuck, and to overcome it and then continue your learning. So this is a common problem that is seen. So another key point is that a neural network cannot find a solution if there isn't one. And it may or may not find a solution if there is one. So sometimes there might be a solution, but the learning algorithm will not be able to find it. So this is similar to what exists in humans. Identical twins have different personalities because they have different neural networks solving problems differently. Everyone has all the normal traits, but the capabilities of those traits differ. So, for example, if we wanted to quantify the ability to sing, the performance of the population would form a bell-shaped curve. So the performance of the population would form this nice bell-shaped curve. So what would happen is that the majority of the people would have an average ability to sing. Some would be above average, so they would have a talent, and very, very few of them would be exceptional or genius. So everyone has many different talents. When at birth, it doesn't come with a manual. So you have to try many different things to discover what your talents are. So there's randomness in the development of the nervous system and the expression of traits, and that ensures that everyone is unique. So another thing that I want to talk about is the effects of drugs. So now in Canada, marijuana is legal, but there's also illegal drugs like angel dust. Angel dust is a glutamate blocker, and glutamate is the most important neurotransmitter in the nervous system. So when you block glutamate, you're disrupting the normal function of neurons. So it's not, basically, those drugs are not dangerous. They simply modify for a short period of time the synaptic strength. But the effects can be dramatic because the network is not functioning properly. So angel dust is a very strong hallucinogenic because it's going to disrupt major systems. If what happens, if your hallucination makes you laugh for the whole period of time, there won't be any problem. A problem arises only if, for certain conditions. One is if you take drugs for long periods of time. If you do that, then you're pushing your nervous system in a different state and it memorizes. So the one function of the nervous system is to memorize, and it will memorize this new state, and that will be a problem. Another problem is if you become afraid during for example, hallucination of angel dust. In this case, after the effects of the angel dust is finished, you will be repeating that scary memory for a long period of time. And it's not the original effect of the drug that is the problem. It's your memory and your replaying that scary situation, that scary experience, that is the problem. So even though you're sober, you're repeating the information that is scary to you. And if you do that for an extended period of time, let's say a month, you will have mental health problems. You cannot have negative feelings like that for a long period of time without causing long-term changes. The last danger is if the drug has withdrawal effects. So if you have withdrawal symptoms, you'll have to suffer through those. So that's all that I wanted to mention about artificial neural networks, which you see are used by Google for speech recognition, facial recognition, and a whole bunch of other tasks that are complicated to write software, but reproduce what humans can do. So the next figure is to talk about real neural networks. So we can describe the neural networks of the nervous system now by describing the complexity of these networks. And so we can classify them into three categories. So we can classify them into simple networks. So the networks of the nervous system can be simple networks. So those would be for reflex behavior. So an example would be the withdrawal reflex. When you accidentally place your hand on a hot surface, the hand will be automatically removed without you thinking about it. The next one are intermediate networks. Those form pre-programmed responses. So you have sensory inputs and you have pre-programmed sensory pre-programmed responses to those sensory inputs. So some of those programs are defined by your genes. So some of them are genetic and form instinctive behavior, like feeding in a newborn baby. That's a very complicated task, but it's pre-programmed in the baby, so it's very simple for the baby to execute. Other ones are learned. So you learn pre-programmed responses, things that you repeat a lot. You generate pre-programmed responses to simplify things. So that would be like a goaltender who, in a sense, reflexively moves his limbs to stop the puck that is coming towards him rapidly. The last type of network would be the complex networks. And those are the ones that allow your language and cognition, which is superior to all other animals and is used for analyzing information. Note that these complex networks have powerful information processing abilities, but the information is acquired over a lifetime as you mature from a child to an adult. So the ability of this system only comes into play as you mature. So our ability to adjust or modify and control these networks is greatest for the complex. So here the amount of voluntary control is shown by the width of this area. So for the complex networks, that's the ones where we have the greatest ability to control. We have less ability to control the intermediate networks, which are the pre-programmed responses. And then we have even less control over the reflex pathways. So when a sensory stimulus is presented to the central nervous system, then the first network will automatically produce a response. So if it's typically, if it's for the simple networks, then you will get a simple reflex. So typically when there's sensory information, if it's appropriate for simple networks, they will activate first. If it's appropriate for intermediate networks, they will activate second. And if it's later on, it's always appropriate for the complex networks. So the order that these areas are recruited is first simple network, then intermediate network, and finally complex networks. So if you were to place your hand on a hot surface, you would have the withdrawal reflex that comes in first. Then the intermediate networks would give you sensory perception of the pain. And finally, the complex networks will allow you to analyze the situation so that you avoid it in the future. Most of what we do is repetitive, and so involves these pre-programmed intermediate networks. So these can be provided through genetic or through learned behavior. So the nervous system is designed to promote survival and reproduction for continuation of the species. So there are numerous pre-programmed networks to handle common situations. So there are genetically derived networks for sensory perception. So these genetically derived networks for sensory perception are used to recreate the external world in a way that you can quantify your surroundings in terms of size, color, temperature, taste, and others. Note that their recreation by your nervous system is a construct for you to easily understand what's going on. So, for example, colors don't exist. They're a construct of your mind to represent differences in light. Light is electromagnetic energy, which we can see for wavelengths between 400 and 700 nanometers, which are part of the visible spectrum. But electromagnetic energy is also microwaves and radio waves and X-rays and gamma rays, which we don't see because they're outside the visible range. Electromagnetic energy has no color, but our nervous system interprets it as color so that it's easy to see the different wavelengths. So once we perceive the sensory input, then there's genetically pre-programmed networks for emotional responses. And those emotional responses are there to help you identify what is important. These are your instincts. If your instincts estimate that it is something good for you, then it gives you a positive feeling. For example, an apple has a pleasant taste. But if it's bad for you, then it gives you a negative feeling. So, for example, a poison has an unpleasant taste. Obviously, these emotions are critical for survival, but it's only an estimate provided by genetic information. So, if you want accurate proof, that only comes from factual knowledge, which you obtain through your complex system using cognition. So, for example, antifreeze tastes sweet, but it's a poison. So, you need to learn that. But this knowledge requires time to acquire. So, you should trust your instincts only if you don't have any factual knowledge to rely on. The genes build the nervous system with pre-programmed urges for survival of the species. Curiosity and imitation are important for children to acquire knowledge from good role models. But two of the most important urges for survival of the species are feeding and reproduction. To get you to eat, the nervous system gives you the feeling of hunger. Furthermore, it has set up taste receptors in the mouth to detect chemical structures, and it provides positive feelings when it estimates something is healthy for you. It'll give you a negative feeling when it estimates something is unhealthy for you. So the nervous system is using positive feelings to encourage you to do things that promote your survival. The nervous system also has pre-programmed networks to encourage reproduction. Here again, it uses positive emotions to guide you. Genetically derived networks give you positive feelings based on visual inputs. So you heard the saying, beauty is in the eyes of the beholder. The sensory system only provides quantitative characteristics on height, size, skin color, facial features, and more. Once that enters the nervous system, then the emotional system provides the feelings of attraction. So a person is not beautiful. It is the observer who finds the person beautiful. It is very important to understand that your feelings are your own. Others might not be attracted by the same characteristics. Furthermore, the nervous system provides one of the most positive feelings when you stroke the reproductive parts of your body. The sensory receptors are the same throughout your body surface, but rubbing elbows won't give you the same positive feeling. So the obvious conclusion is that the strategy of the nervous system is to guide us in the right direction by providing positive feelings. Negative feelings are an estimate that you're going in the wrong direction. Experiencing negative emotions for long periods of time, for example, over a month, can lead to mental health problems, which will be covered briefly in this course. But you must remember that emotions are genetically derived estimates of importance that must be verified for accuracy using objective, factual information. So factual information is provided by the sensory system. You can see and report the height, skin color, and posture of a person. Anyone looking at that person would see the same features and they would agree with you. That is objective, factual information. However, if you say the person is beautiful, then this is an estimate from your own emotional system. Not everyone would have the same feelings. So this is not objective, factual information. Your complex networks offer you some control over your emotions. So you can dampen the fear of death while watching a movie when you take the time to realize that you're not in danger. So when your negative emotions are causing you harm, you could dampen them to protect from mental health problems. It's like when toast are burning and the fire alarm goes off. You rush and identify the problem and solve it by removing the toast, and you unplug the alarm because it's driving you crazy. Negative emotions are like an alarm. They are not a solution. They're just a cue for you to take care of a problem. So you must use your cognitive abilities to solve the problem. So this ends this introductory lecture. Thank you very much, and I'll see you next time.